Hi, everyone. Thanks a lot for joining IST for this webinar on ESCC-qualified platinum temperature sensors for space applications. This meeting will be recorded and posted to YouTube later on. So if you want to share it with any of your colleagues or anything, I'll send out the slides and the recording link when it's available. It looks like I might have set up a lobby on this meeting, so occasionally I might need to pause to let people in. Hopefully I fixed that. All right, but again, thanks for joining us. So here's just a quick overview of what we'll cover. I'll start with an intro to platinum RTDs. Then we'll compare the ESCC qualified RTDs with off-the-shelf components. We'll then go in depth with the ESCC detail spec for thin film platinum RTDs, and we'll review some of the relevant screening tests. At the end, we'll wrap up with a Q&A, so feel free to submit your questions at any time in the chat, and I'll go through them at the end of the presentation. I'll also share my contact information if there's a question that I can't address today, or you need any additional information later on. Okay. So first, just a little bit about us. Innovative Sensor Technology IST AG designs and manufactures thin and thick film physical, chemical, and biological sensors. So here you can see our headquarter facility in Switzerland, where we've been in operation for just over 30 years. And as of this year, we have around 500 employees across all locations. Along with our standard product offerings, we also make sensors which are custom tailored to our customers' requirements. So here's the product lineup. First, core competency of IST on the left, and what we're talking about today, the platinum RTD temperature sensors. We also have nickel RTDs, digital temperature modules, thick film microheaters, gas and liquid thermal mass flow sensors, capacitive humidity sensors and modules, electrical conductivity sensors, and enzymatic biosensors. Some unique newer offerings are the infrared emitters, sensors for force, pressure, surface tension, and torque measurement, and also kits for RNA extraction. But today we're focusing just on temperature. So let's go more in depth about resistance temperature detectors, or RTDs. So for thin films, here's what they generally look like. We start with an aluminum oxide substrate, then we sputter a thin metallic layer on the top side. This is usually platinum or nickel. Then using spin coating, photolithography, and etching, we shape the meander structure, which will act as the temperature sensitive resistor. The meander is then laser trimmed to the customer specified nominal resistance. Then a thick film glass passivation paste is applied over the top. Finally, the wires are welded using a resistance weld on each pad, and another paste is applied and hardened to protect the wire weld area. At the end, the sensors are measured and sorted into the different accuracy classes. So you might be familiar with IEC 60751 class A, B, AA. If you want to learn more about those, we have a temperature webinar on our YouTube channel, which goes through those. So the operating principle of these RTDs is pretty straightforward. As temperature increases, the resistance also increases. And these can be customized in a number of different ways, but today we'll focus on wire customization, in particular 2- and 4-wire cable extensions. So we know that there are plenty of ways to measure temperature. Lots of pros and cons with each. So we want to know what makes thin film RTDs beneficial. First, they offer very good long-term stability and they're very vibration resistant. They can also be configured with different materials and wire types to cover broad temperature ranges up to 1,000 degrees C. On the bottom right, we have an example of a traditional wire wound RTD. These feature a very thin wire wrapped around a cylindrical or rectangular substrate. These wires can become damaged with vibration and repeated thermal cycles, especially when we're working with high resistance RTDs since the wire would be extra thin. At the top right, we have a thin film platinum RTD. The one pictured here is one of the ESCC qualified elements. With these, the platinum is physically bonded to the substrate with the sputtering process, so there's less of a concern for damage from thermal cycling or vibration. Thin film platinum RTDs have been utilized in space for many years. Here are a couple of examples where IST provided platinum resistors for space missions. On the left, we have the Rosetta mission, where a thin film RTD meander was implemented on a spectrometer device. We have it here circled in red on the left. And next, on the right, we have the TSAT laser communication terminal. In this case, a thin film style RTD with an integrated heater was developed for thermal control of a laser crystal in the device. So how did IST go down the road of ESCC qualification with ESA? At the time, there was no supplier of space-qualified PTC-type thin film temperature sensors. By PTC, I mean positive temperature coefficient, so increasing resistance with temperature. With over 10 years of space heritage and temperature measurement, it made sense to begin the process of qualification. The thin film platinum technology offers several advantages and could be implemented well in many space and other high reliability applications. So having supplied thin film sensors over years for various satellite manufacturers, ESA selected IST AG as a partner for the qualification of thin film platinum RTDs. Over 4 years with the support of ESA, we achieved ESCC qualification for 10 different temperature variants, 10 different sensor variants covering 2 temperature ranges and 5 nominal resistances. So this image we have here is the profile that you'll see for all of these sensors. They all have the same form factor. The only difference is the temperature rating on some or the nominal resistance, but the chips overall look identical, and they're based on an existing chip size that's very popular for us, which is this 2.3 long by 2 wide chip size. So the result of the qualification efforts was the ESCC detail specification number 4006-15. Originally, this just covered the base elements with short wires like I pictured before. But as of earlier this year, it also includes the extension cable. So previously, we would add the extensions, but only the base sensor was considered to be space qualified. Along with the ESCC qualified flight models, we also offer engineering models for initial evaluation. Here's an overview of the different base sensor variants that we have on the ESA QPL. We have increasing resistance as we go down the list from 100 to 2000 ohms. The higher the nominal resistance, the bigger the resistance increase you'll get per degree Celsius. If you're doing a 2-wire measurement with long cables, the higher resistance can certainly be beneficial because the wire resistance offset will have less of an effect on your overall resistance measurement. The measuring current should be kept lower with the higher resistance chips to avoid sensor self-heating effects. I mentioned some accuracy classes before. In this case, all of these chips are Class B according to the IEC 60751 norm for thin film platinum elements. For enhanced accuracy, we can perform a measurement service on request and provide individual curve coefficients for each sensor. So these extensions are performed with laser welding, and we typically add a TFE-R shrink tube around the weld joints and then again around both wires here. You can see in blue. Some additional ones are added to protect the twisting of the cables. The insulation wire that we're using is also ESCC qualified according to detail spec 3901-19. And from left to right, we have a basic 2-wire extension, then a twisted pair, 2-wire with shielding, then a twisted quad, and 4-wire with shielding. So if your electronics support it, a 4-wire measurement will always give you the most accurate result, since you can subtract the wire resistance from your overall measurement and you're left with the resistance of the RTD chip itself. So what are the key benefits of using ESCC qualified parts compared with using any other RTD off the shelf? First, the ESCC system is internationally recognized, so using parts from their QPL can allow for simpler part approval. These parts are also the preferred parts in ESA programs, and they've been evaluated for reliability for use in space. Their technologies, design, and manufacture are well-defined and controlled. And lastly, the manufacturers that are listed on the QML with ESA have had their supply chains audited by the ESCC executive. So here we see the screening tests as outlined in the general spec 4006 for thermistors. These are performed on all of our qualified elements. IST also performs an extensive set of periodic tests to achieve requalification with ESA. The test plan follows the same general flow as the general spec 4006, and the detail spec for thin films lists any deviations from the testing charts. This includes some tests which are skipped because they were deemed unnecessary for thin film elements, and so they're crossed out here. I'm going to highlight a few tests from chart 4, F4. So I'll just clarify here, chart F3, these are performed on all elements. Chart F4, some of these tests are periodic. So for now, I'm going to be going through the periodic ones from chart F4. So here we have a terminal connection strength test on the left. We test the pulling force needed for plastic deformation, or basically for the wires to come off. So we pull by both leads together on the short wire RTD, and we see failure at around 10 newtons when pulling in the parallel direction and around 8.5 newtons when pulling perpendicularly. The general specification deems 2 newtons acceptable. On the right side, we have a high voltage test. Pictured here, we have the 100 ohm element. You can see we're really heating it up and it's glowing bright. We're trying to push it to failure. This sensor was able to withstand over 35 volts, over 60 milliamps, and over 2.3 watts. We note here that according to the detail spec, the sensor is only required to withstand 20 milliwatts. With our tests, we were actually unable to destroy the 1000 ohm variant. So pictured here, we have the 100, but we perform these tests on both the 100 and the 1000 as part of the periodic requalification. Next up, we have a test for drift after thermal shock. In this case, the sensors are repeatedly transferred between negative 65 Celsius and plus 200 Celsius. Measurements are taken before and after, and as we show here on the right, there's barely any drift observed for all the different sensors that we've tested. Next, we have a moisture resistance test. Here we measure the resistance before and after the elements are repeatedly exposed to high humidity. And then they're dried for a final measurement. Again, here we see very minimal drift. Next, we look at the drift after storage at a low temperature. So this is sometimes an important factor when you're working in a space application. You'll be dealing with pretty low temperatures. In our case, we're always looking to rate these sensors down to negative 200 C. So here the sensors are kept in liquid nitrogen, so negative 196 C for 168 hours. Then a 2-bath measurement is performed, like with all the other tests. And again, we observe barely any drift. Finally, we check how these sensors perform after 70,000 cycles between negative 196, so liquid nitrogen, and plus 200 C. The motivation behind this is an ISS example. So we have a 20-year-long mission circumnavigating the Earth 16 times per day. So we're going to be seeing these cycles between around negative 200 and plus 200. So that's where we get the 70,000 cycle number from. So the way we do this is in 30 seconds, the sensor is heated up to 150 C or higher. This is done by sensor self-heating. So we drive a current, a pretty high current through the sensor to heat it up. Then over 30 seconds, we apply no current and we let it cool to negative 150 C or below using liquid nitrogen. And this is repeated 70,000 times, and it's checked after several cycle counts. So here we have 20,000, 50,000, 70,000, and we even take it a step further to 100,000 cycles. And again, we see there's very little drift. We have here the deviation in millikelvin, and this is from the two-bath test, and this is deviation in millikelvin of the resistance at 0. So we're extrapolating down to 0, and we see very little drift. So the USL and LSL lines here are the allowable limits according to the detail spec. All right, in conclusion, the thin film RTDs offer better long-term stability and vibration resistance compared with some other sensor types. These ESCC-qualified thin film variants are available in 10 base variants with 5 extension types. And the qualified FMs undergo extensive pre-screening and are shipped with traceable lot date codes. And as I mentioned on a previous slide, we also have engineering models or EMs available, even with extensions, if you're looking to do some initial testing with those before you're ready to go for the flight models for in-flight use. So thanks for watching. If you have questions, please write them in the chat and we can discuss them. You can also get in touch with me directly. I'll drop my contact info in the chat. So most of the space inquiries that come in for the Americas would go through me. So you can contact me directly if you have any questions or you need a quote or any additional information. If you're located in Europe or anywhere else in the world, I'll give you the contact information for my coworker Omar Sachet, based at our headquarters in Switzerland. So I'm dropping my info in the chat now, and I'll also follow up with these slides and the recording link once it's available by email, as well as some relevant links, including the detail spec, the generic spec, and the qualified parts list. So you'll have all the information. And also, I'll give you maybe I can increase the size of the camera somehow. Let's see. I can show you what an extended sensor typically looks like. I have a display sample here. Hopefully my image is showing up large enough. So we have the RTD component that I mentioned before. It's 2 by 2.3 millimeters. Thickness is about 1.1 millimeters. So the substrate is 650 microns, and then we have the wires welded on top, the short wires. And we've extended with a 4-wire cable. So we have 2 welds on each of the short leads, covered by the TFER shrink tube. And this option actually has the shielding, so you can see the terminals here. So we typically ship it on a card like this in ESD compliant packaging, like these bags. And you'll see the ESA logo right next to ours on the label, so you know it has the stamp of approval from the qualification batch. So we have a question. Are the ESCC sensors built with any different materials than the standard thin film elements, or is the difference primarily just the testing and qualification? That's a a really good question. Let me go back to the slide on the materials. So these are based on an existing RTD design that we already had. It looks exactly the same as what we see here. This, oh, I'm not sharing the screen. Let me do that first. Sorry about that. So on the top right, we have a typical RTD. We call this our 232 chip size with a 7W wire, meaning pure platinum. The materials are exactly the same as what we use for our regular RTDs. There is a slight design difference with the mask that we're using for the resistive element that's sputtered on the top. So it's designed in a way that will be less prone to ESD damage. So it's something with the design of the resistor itself and the passivation layer. It's slightly different than the standard 232 chip, but it's the same materials involved. So aluminum oxide, platinum. This is the 3850 platinum that's pretty standard in Europe and mostly around the world. This passivation glass, which we develop in-house, we have different glasses available for different temperature ranges. So in this case, the glass is the same as what you would see on our 7W series. So if you go to our website and look at the downloads and then 700-degree sensors, it's basically the same thing. If you look at the 232 chip, the core difference is that, as I mentioned, slightly different mask that we're using, so a slightly different shape of the resistor, and we're adding in all these screening tests. So if you were to get a engineering model of this sensor and something from our standard catalog, they should operate exactly the same way. We just consider this one to be slightly more robust. Again, not because of material differences, but because of slight design differences. I hope that helps. And then the wires that we're using here, this 390119, it has a few different insulation layers. It's like a expanded PTFE and then polyimide. And this isn't something we would typically work with on most of our other RTDs. We could, on request, we could add it to anything, but we typically only use this in space applications. But it would be good for any cryogenic application since it works well down to -200. But besides that, no major differences in the structure or materials. Okay. Again, feel free to email me, thomas.hall@ist-ag.com anytime if you have questions. And thank you again for joining. We appreciate it, and we'll send out some more information once the recording is published. All right. Thanks again. Wishing everyone a nice afternoon or morning wherever you are.